You know, every time you take a medicine, you're kicking off this incredible secret journey right inside your own body. So today, we're going to pull back the curtain on that journey and see what's really going on.
I mean, really, think about it. You swallow a pill for a headache, right? And a little while later, poof, you feel better. But what on earth happens in between? Where does it go? And how does your body handle it? It's something we all do, but we almost never stop to think about the process itself.
Well, that tiny pill doesn't just magically teleport to where it's needed. Not at all. It actually undertakes this amazing journey, almost like a tiny explorer navigating the huge internal landscape of your body. And this hidden story, this biography of a drug's life and death inside us, actually has a scientific name. And that name is pharmacokinetics. Now, put simply, it's the study of what the body does to the drug. It's not about what the drug does to you. That's a whole different field called pharmacodynamics. Nope, pharmacokinetics is all about the path the drug takes, from the moment you take it to the moment it's gone.
So, what does this journey actually look like? Well, you might be surprised to learn that scientists have it all mapped out, and it follows a really organized four-step itinerary. It's so common, in fact, that it has its own acronym, ADME.
Absorption, distribution, metabolism, and excretion. These 4 stages, they make up the entire life cycle of a drug inside your body. So let's dive in and break down exactly what happens at each stop on this wild ride.
Okay, first up is absorption. You can think of this as the moment the drug gets onto the main highway, your bloodstream, or what scientists call the systemic circulation. For a pill you swallow, this means it's got to pass through the wall of your gut to get into your blood and start its trip. So once it's on that highway, it's time for distribution. The bloodstream just carries the drug all over your body. This lets it travel through all the different fluids and tissues to finally reach its destination. You know, whether that's a receptor in your brain or an inflamed joint in your knee.
From there, the drug arrives at the body's incredible chemical processing plant, which is usually the liver. This stage is called metabolism. So here, the body recognizes the drug as a foreign substance, and it starts to break it down into different components, which we call metabolites. This process basically deactivates the drug and gets it ready for removal.
And the whole journey wraps up with excretion. This is the final cleanup phase. The original drug and its now harmless metabolites are kicked out of the body, most of the time through the kidneys and into your urine. And just like that, the journey is complete.
Okay, so we have the map, those 4 main stages. But how do scientists actually track a drug's progress in real time? I mean, you can't exactly put a turny little GPS tracker on a molecule, right? Well, instead, they rely on some really clever measurements to follow its path and figure out its impact.
What they do is they take blood samples at different times after a drug is given. By measuring how much drug is in the plasma, they can create a curve that acts just like that GPS tracker. It shows them not only where the drug is in its journey, but exactly how much of it is there at any given moment.
One of the most important things they look for on that curve is something called Cmax, or peak concentration. This is the absolute highest point the drug reaches, the moment of its strongest presence in your body. It tells scientists about the drug's maximum intensity, which is absolutely crucial for knowing if a dose is strong enough to actually work.
And another vital metric is the drug's half-life. This is just the time it takes for your body to get rid of half of the drug. And this number, it's fundamental to your prescription. It's the reason you take a pill once a day versus every 4 hours. Why? Well, it's all about keeping the drug's concentration in that sweet spot where it's both effective and safe. If you get the timing wrong, the level could drop too low to work or climb high enough to be toxic.
And all this brings us to bioavailability, which is basically just asking how much of the drug actually makes it to the bloodstream to do its job. See, an intravenous or IV injection, it bypasses that whole absorption step, delivering the drug directly onto the highway for 100% bioavailability. A pill, on the other hand, has to survive the really harsh environment of your stomach and gut first, so a much smaller fraction often makes it into circulation.
Measuring the journey is one thing, but what if we could actually predict it? That's exactly where pharmacokinetic models come in. You can think of them as predictive maps that forecast a drug's behavior.
Look, the human body is just ridiculously complex. So to make sense of it all, scientists create these simplified models. They're like mathematical maps that help them understand how a new drug might behave, and that lets them make much better predictions about safety and dosage long before it ever reaches a pharmacy.
And these models range from pretty simple to incredibly complex. A single compartment model, for example, treats the whole body like one big, well-mixed room.
It's useful simplification for a lot of drugs, but for drugs that spread out unevenly, a multi-compartment model is way more realistic. It sees the body as a house with many different rooms, organs, tissues, fat, where the drug can enter and leave at different speeds. Choosing the right mat is just critical for predicting a drug's behavior accurately and keeping patients safe.
So we've covered the journey, the measurements, the maps, but why is all this so important in the real world? Why does pharmacokinetics matter so much?
Because this science is, without a doubt, the foundation of modern medicine. It's how doctors figure out the right dose of the right drug for the right patient. Remember, this is all about what the body does to the drug. Getting that part wrong can mean a treatment that just doesn't work, or even worse, one that causes serious harm.
Let me give you a perfect example, the drug cyclosporin. It was a huge breakthrough for preventing organ rejection after transplants, but it was also highly toxic to the kidneys. So toxic, in fact, that it was almost abandoned. But then came pharmacokinetics. By carefully monitoring the drug's concentration in each patient's blood, doctors could fine-tune the dose, keeping it high enough to work, but low enough to be safe. This science single-handedly turned a dangerous compound into a life-saving tool.
And cyclosporin is definitely not the only one. This kind of monitoring is essential for so many of our most critical medications, from anti-epileptics to powerful antibiotics and heart medications. For these drugs, the line between an effective dose and a toxic one is incredibly thin. This science is what helps doctors and patients walk that line safely every single day.
Which leaves us with a really fascinating thought. We've gone from a basic 4-step map to these incredibly sophisticated models of a drug's journey. As our understanding gets even more precise, we're moving closer and closer to an era of truly personalized medicine, where your next prescription isn't just for the average person, but is tailored perfectly and only for you.